Hello, Eastview Scholars. Welcome to another edition of Sharp Shorts. We recently just talked about electron configurations, and we made a mention during that those final valence electrons, that final electron configuration and the valence electrons at the end were the key, because that is, we know protons identify what the atom is, neutrons will help identify which isotope you're working with. The electrons, specifically the valence electrons, do all the work, which, as you can see here, allows to understand whether it's ionically bonded, covalently bonded, and how to name and write chemical compounds and reactions, which is the key to this course. So, what are valence electrons? Well, they are the ones, and specifically they are the s and p orbitals in the very outermost energy level, that first principal quantum number. What row is it in a periodic table? 1, 2, 3, 4, 5, 6, 7. Which ones are the most? And the S and P's are the ones that we work with, because those are the ones that, other than the first few very small atoms, everybody has. All the elements have. And so those are the key ones that do the interacting. As it says here, responsible for the bonding and stuff. Now, on most periodic tables, there will be a Roman numeral, sometimes just a number, usually followed by the letter A or B. We're not going to worry about the A or B, but that's it. So instead of having to go through writing out electron configurations and figuring out which ones you have, or hopefully if you've gotten used to the S, P, D, and F organization of the periodic table, you can find that final electron configuration. But that just helps you know which valence electrons it has. And really what you're looking at is what ions will they form. Elements themselves are neutral, and they will not react as neutral entities. So they form ions is a method of being reactive. And the magic number of that, since an s orbital can hold 2 electrons, and a p orbital can hold 6 electrons. Okay. The magic number then is 8. And that's why the noble gases don't react. They have 2 s's, 6 p's, 8 electrons. They're in the very farthest column, number 18. And they are unreactive. They don't drop electrons, pick up electrons, share electrons, do any type of bonding or reacting. All the other elements, the reason that they might be, whether they're ionically forming an ionic charge by dropping or picking up electrons, or forming a covalent bond by sharing their electrons, all they're trying to do is get their s and p orbitals, whatever outermost one that is, into a stable octet, it's called, to achieve the same stable formation as a noble gas. Okay, and that's what leads to bonding and forming reactions. They are literally trying to become stable like noble gases. Okay, so here's the neutral chlorine. Here's how I would write its ionic form, and whether we look through these or not, we'll just work through forming some ions. And let's go to our periodic table here. Okay, now you can see in this drawing that I have here, it doesn't have Roman numerals, it just has normal numerals above, 1 through 8. Now we are going to stay out of, until we start naming compounds, we're going to stay out of the D block. Okay, with that D orbital, it can cause some changes, and really what happens in here is there are multiple possible charges for these things, so we're going to stay out of there. We're going to concentrate on the S block and the P block over here, because they're pretty standard. Now what you can see here is that other than helium, which is small and only has one S, you can see all the rest of these noble gases have 8 electrons in their outermost s and p orbital. Okay, so these numbers tell you can see these are all the S1s. They have 1 valence electron. These are all S2. They have 2 valence electrons. Here you have an S2 and a P1. They have 3 valence electrons. Here you have, we skip the 4s because carbon and silicon don't, well, silicon might, but carbon only covalently bonds, and mainly so does silicon. Here you can see 5. They have 2 S's, 3 P's, 2 S's, 4 P's, 2 S's, 5 P's, so 7 valence electrons, 6 and 5. What does that mean? Well, let's take sodium, for example. Okay, sodium as a neutral element will have, by atomic number 11, by definition it has 11 protons. As a neutral atom then, it will also have 11 electrons. Now, it has 1 valence electron in the 3s1 outermost orbital. It has a choice then. Since it wants that stable full shell, it can try and pick up 7 electrons and have the same configuration as argon. Or, what might be easier is if I dump this 1 electron and get rid of it, then I will have a stable configuration, only have 10 electrons, and have a stable configuration like neon. Because, again, since everything started at 1s and filled out, it was full to this point, and then it picked up 1 extra to be sodium. So that's what it'll do. If I get rid of 1 electron, since my proton number will never change, ever, and that'll stay at 11, and I've now gotten rid of electrons, so I only have 10 electrons, I'm going to be a +1 charge. And that's the ion it will form. Same thing if I went over to the other side here with chlorine. Okay, if I look at chlorine itself, and it's got 7 valence electrons, and it started with 17 protons and 17 electrons, okay, 17 positives, 17 negatives, because it was neutral. Okay, this number can't change. Okay, so it will always stay at 17 protons. Now, the decision is, here I have 7. If I pick up 1 electron, I can have a filled shell, filled octet, and simulate the noble gas configuration of argon. Or my other option would be to try and dump all 7 electrons and look like neon. But why would I? That would be too much effort. So I will pick up that extra electron. Now I have 18 electrons. So my charge is a -1. Okay. And you can see with sodium and everything in column 1, they're the same family. They'll have same properties because they have the same valence electron shell look, and they will all have a +1 charge. Here in column 2 with beryllium and magnesium and calcium, because they have 2 electrons, it'll be easier to dump 2 electrons, and so all of these will have a +2 charge. Here, boron and aluminum have 3 valence electrons. It'll be easier to dump 3 than try and pick up 5, so they'll all have a +3. Here with nitrogen, phosphorus, they already have 5 electrons. It's easier to pick up 3 electrons, heading that way, fill out my shell, so these will all have a -3 charge. Oxygen, sulfur, selenium, all have a -2 charge because it's easier to pick up 2 electrons. Fluorine, chlorine, bromine, halogens, all will pick up 1 electron and get to 8. So these will all have a -1 charge. Now when I formed an ion, here I've got a positive sodium, it's got its ion, this negative chlorine, opposites attract, just ask my wife. So the positive and the negative, so you've got a metal and a non-metal that will form an ionic bond to form sodium chloride because they are attracted by their positive and negative charges. And that was the importance of electron configurations and properties of the table and everything else. You can see metals are, and one of the properties of metals was it likes to lose electrons, making it a positive ion. One of the properties of nonmetals was it likes to gain electrons, forming negative ions. So metals and nonmetals love to bond together in ionic bonds. Now, since these are all positive because they like to dump electrons, they're not going to form an ionic bond together. In fact, they're not going to do anything. Metals do mix to make alloys, but then they don't bond. They make mixtures. Nonmetals here, these are mainly things that are in your body and stuff like that. Now, they're both negative when they form ions, and so they won't form an ionic bond. But if they don't form the ions and just share their electrons, that will make a covalent bond. And of course, our noble gases here won't form any bonds with anything at all. Anyhow, that's a quick look at how to make ions. Scholar on, Eastview.